In this video, we'll be talking a bit about how to add, subtract, and multiply complex numbers. So addition and subtraction of complex numbers are pretty straightforward. Namely, for two complex numbers, a plus bi and c plus di, the sum and difference are going to be, well, so if you want to add them, aka the sum, if you want to add two complex numbers, all we have to do is add their real parts and then add their imaginary parts together, okay? The way to think about this in practice is, well, never mind that. Further, if we want to do the difference, namely a plus bi minus c plus di, all we would have to do is subtract their real parts and then subtract their imaginary parts, okay? In practice, what this really looks like is adding and subtracting like terms, where we treat I as just a variable, okay? Now we know it's not actually a variable, but we're going to kind of treat it like it is one for the purpose of the algebra we're going to do. Namely, if we wanted to do 4 plus 7i plus 1 minus 6i, I could match them up like this, but it's much easier than that. Let's write as 4 plus 7i plus 1 minus 6i, and then let's combine like terms. The 4 and the 1 come together to give me 5, and then the 7i and the minus 6i come together to give me just 1i, or just I if you prefer. Similarly here, we can do the same thing using all of our similar rules of algebra. 3i, the negative would distribute through, so we'd have negative times negative 2, which is positive 2, minus 3i, minus 2, minus 5i. And then we combine like terms. The 3i's would cancel, the 2's would cancel, and we just end up with a negative 5i. Or if you prefer, 0 minus 5i. So here, this is a purely imaginary number. If you see the last video, you'll understand what that means. Now it's time for you to go ahead and try some examples. So go ahead and perform the following addition and subtractions of complex numbers. On the count of 3, I'll reveal all the solutions. 1, 2, 3. So up here, this one's pretty standard. We just drop the parentheses, add up like terms. Notice with all of these, I have them in standard form. That is of the form a plus bi. Here a is 12, here b is negative 1. Here, remember to distribute the negative. Here a would be negative 2 and b would be 7. Okay, again, standard form is a plus bi. Okay. And then here we go ahead, we do distributing. We'll see that all the real parts will cancel and we just end up with I. So here a would be 0, b would be 1. And then here both a and b are 0 because all of the real parts and all the imaginary parts actually cancel out with each other. And so this brings us to multiplication. The important thing about the multiplication is that, and you could write a similar formula if you wanted to with the addition and subtract, like you did with addition and subtraction, but really what this all comes down to is foiling, okay, aka first, outer, inner, last. This is easy for the first problem because we have that this is really, we only have a real part here, so we're just distributing through. So this would be negative 8 plus 4 times 3i is 12i, and so that would be our solution. Here we have to actually FOIL out. Foiling out, we get first, so 2 times 4, which is 8. Outer, which is 2 times 3i, which is 6i. Inner, which is negative 4i. And last, which is negative I and 3i. So let's write 3i squared. Here, though, you got to be a little bit careful because you know 3i squared, since we know I is defined to be the square root of negative 1, I squared is really negative 1, okay? So, because of that, we actually have that this is negative 1, so that becomes negative 3, so we have 8. These combine together to give me plus 2i, But then here we actually have plus 3, because a negative negative give me a positive. In other words, what we actually have here is 11 plus 2i. And again, I'm writing all of these in standard form. Here you could FOIL this out, but what you'll notice is these are actually conjugates of each other, which always creates a difference of squares, right? Let's go ahead and see that though first. So 9 outer minus 6i inner plus 6i last minus 4i squared. And again, creates a difference of squares because the middle terms will kill each other. Okay, it's that difference of sign that does that. Well then, here we see minus 4i squared. And so we have 9 minus, again, the I squared will become a negative 1. And so we actually have 9 plus 4, which is 13. Again, an interesting thing here, though, to notice is that multiplication of complex conjugates, right? That is a complex number and its conjugate always gives a real number. Real number. We'll talk more about that in the next video, but it's worth noting right now. Anyways, moving on to the next example here. Don't forget that squaring means we're really writing this as 3 plus 2i times 3 plus 2i. Do not distribute the square. Squares don't distribute across addition. 3 and 3 will give me 9 plus outer, so 6i plus inner, 6i plus last, 4i squared. Again, the I squared is negative 1. So we actually have here that is negative 4. So we have 5 plus 12i. Now it's time to have you try some examples. So go ahead and perform each of the following operations and write the result in standard form. On the count of 3, I'll reveal the answer. 1, 2, 3. So here are the solutions. You'll notice that these are very similar to the last problems I worked. So yeah. A natural sort of last lingering question is, what about a division? Because we talked about addition, subtraction, and multiplication. Division is possible, but it's going to be a little different than perhaps what you think. Namely, as we've seen, that division is kind of hard to do with algebra in general. We're going to see that the best way to deal with it will involve complex conjugates and rational and multiplying denominators by its conjugate, the numerator denominator by the conjugate. Anyways, don't worry about any of that because we'll cover that in the next video. For more practice in working with these operations on complex numbers, be sure to see page 150 of the textbook and work problems 23 through 38. In our next video, we'll be talking about complex conjugates.